Well, hello and welcome to our third Thursday webinar. I am Tom Sandry, and today we're going to be talking about resistance testing of busway systems. Did it pass or did it fail? Now, commercial and industrial distribution systems use various methods to conduct electrical energy. These methods often include heavy conductors run in trays or in conduit. And cables and conduit assemblies are costly and time-consuming to install. Once installed, they are also very difficult to change out. To eliminate these shortcomings, power is often distributed using enclosed bus bars. Now, this is referred to as a busway or bus duct. A bus bar is a conductor that serves as a common connection for two or more circuits. It is represented schematically by a straight line with several connections made to it. Busway bus bars are made of either aluminum or copper. Now, NEMA definition. A busway is defined by the National Electrical Manufacturers Association, or NEMA, as a prefabricated electrical distribution system consisting of bus bars in a protective enclosure, including straight lengths, fittings, devices, and accessories. Busway includes bus bars, an insulating and/or support material, and a housing. The NEMA phase arrangement of bars. Bus bars are required by NEMA to have phases in sequence, so an installer will find the same fixed phase arrangement at each termination point. As we see in the vertical, typically working from left to right, A phase, B phase, C phase. In horizontal, working from top bar down, A phase, B phase, C phase, and N if there was a neutral. The diagram shown illustrates the accepted NEMA phase arrangements. Now, the number of bars depends on the number of phases on the power supply and whether a neutral or ground is used. So again, here we see a three-wire, three-phase with A, B, C phase and ground. Or we see an A, B, C, and neutral in a four-wire configuration with ground and obviously the fourth bar representing the neutral. Now let's take a look at low voltage versus medium voltage structures. As we can see in this example shown, there is considerable difference in the physical construction of low voltage, or sometimes called sandwich style busway, and medium voltage, or sometimes referred to as segregated bus duct. Now, electrical tests that are recommended or called out. Here we'll refer to the NETA-Recommended electrical tests. And first we'll take a look at the acceptance testing specifications outlined in the 2021 ATS manual. Perform resistance measurements through bolted connections and bus joints with a low resistance ohm meter in accordance with section 7.4.A.5.1. Perform insulation resistance tests on each busway for 1 minute phase to phase and phase to ground. Apply voltage in accordance with manufacturer's published data. In the absence of manufacturer's data, use table 100.1 of the ATS manual. Perform a dielectric withstand voltage test on each busway, phase to phase, with phases not under test grounded, in accordance with manufacturer's published data. In the absence of manufacturer's data, use table 100.17. Where no DC test value is shown in table 100.17, an AC value shall be used. The test voltage shall be applied for 1 minute. Continuing on in the recommended electrical tests, perform a contact resistance test on each connection point of uninsulated busway or insulated busway. Measure resistance of assembled busway sections and compare values with the adjacent phases. Perform phasing tests on each busway tie section energized by separate sources. Tests must be performed from their permanent sources. Verify operation of busway space heaters. Perform online partial discharge survey in accordance with Section 11 of the ATS manual. Now, this is an optional call-out. Now, let's also take a look at the NETA recommendations that are outlined in the maintenance testing specifications, the 2019 MTS manual. Again, we see perform resistance measurements through bolted connections and bus joints with a low resistance ohm meter in accordance with Section 7.4.A.3.1. Perform insulation resistance tests on each busway for 1 minute, phase to phase and phase to ground. Apply voltage in accordance with manufacturer's published data. In the absence of manufacturer's published data, we refer to Table 100.1. Perform a dielectric withstand voltage test on each busway, phase to ground, with phases not under test grounded in accordance with manufacturer's published data. If manufacturer has no recommendation for this test, it shall be in accordance with Table 100.17. Where no DC test value is shown in Table 100.17, AC value shall be used. The test voltage shall be applied for 1 minute. Continuing on in the MTS recommendations, perform a contact resistance test on each connection point of uninsulated busway. On insulated busway, measure resistance of assembled busway sections and compare values with the adjacent phases. Now, in the maintenance manual, we see this as an optional test. As we saw in the acceptance testing standards, we saw this as a required test. Verify operation of busway space heaters. Perform online partial discharge survey in accordance with Section 11 of the MTS document. And once again, this is an optional call-out. Now, during this webinar, obviously by the title of the webinar, we will be focusing on resistance measurements. And when we really are looking at the resistance measurements on the busway, as we see, they fall into two different categories. For instance, we see the perform resistance measurements through bolted connections and bus joints with a low resistance ohm meter. So in this resistance measurement, we're really focusing on continuity of the circuit, how well it's going to pass current, or we're looking at how low the resistance is along the current traveling path. Now, we also have perform insulation resistance tests on each busway, phase to phase and phase to ground. Now, this test is going to use something like an insulation resistance test set or megometer, and we're going to look at how good the isolation is between bus bars and frame or ground and between bus bars phase to phase. Again, here we're looking for how well we isolate the flow of current between 2 points where there should be no current flow. Now, the total resistance in a series circuit is equal to the sum of all the parts of that circuit, as shown in the equation. Resistance, or total resistance in ohms, is going to equal the resistance of R1 plus the resistance of R2 plus the resistance of R3, and so on and so forth. So again, resistances that are in series will simply add to one another. But now let's also understand what happens when we measure resistances that are in parallel. When resistors are placed in parallel, the voltage across the resistors is the same, but the current through each one is inversely proportional to its resistance. The total resistance in a parallel circuit can be found by using the equation. The resistance in megohms would equal the reciprocal of the total resistance, which would also equal the reciprocal of resistance R1 plus the reciprocal of resistance R2 plus the reciprocal of resistance R3, 4, and so on. So, let's take a look at actually performing the series test, or the continuity portion of the resistance test. Now here we would use a standard product like a micro-ohm-meter, sometimes referred to as a DLRO, or digital low resistance ohm meter. Other terminology is referred to as a ductor. Now here it's a 4-terminal measurement. 2 of the connections is current in, followed by a return current, or current positive and current negative. So we see that the C1 connects to one end of the resistance that we're trying to measure. The C2 connects to the other end. We create a loop current going through the specimen that we're measuring. And now there are 2 posts that are dedicated as basic potential meter, or a voltmeter. So here we measure the voltage drop across the resistive specimen that we're testing, and that will provide a micro-ohm measurement, or a very low resistance measurement, showing us just how good the continuity is. Now, a DLRO, ductor, or micro-ohm meter being a 4-terminal measurement, the instrument is metering the output current. Therefore, if the test leads were to change length, this does not become a factor in the measurement. The current flowing through the entire loop is always a measured current in this style of an instrument. And then the voltage drop, or the potential, is also a measured value. So the measurement becomes independent of lead lengths, connection types, etc. Since we're always dealing with measured values, we're always going to obtain the most accurate measurement of the actual resistance or specimen that we are interested in, regardless of lead or connection style. Now here, if we were to test, for instance, just a single bus, okay, we would go ahead, connect the instrument as shown in the diagram. And if we were to now connect that bus section into another bus section, well, obviously we'd be interested in measuring the connection point, how good an electrical contact as they're bolted together. But now these 2 resistances would add as series. So our total measurement here would be basically the resistance of bus segment 1 plus the bolted connection and the resistance of section R2, or bus section 2, and so on and so forth as we would add bus sections. Now, when we get long assembled busway, how do we hook up the micro-ohm meter? Well, here let's start with the current path. So we would take our C1 lead and connect it to one of the bus bars. Now that current is going to travel through bus segment 1, through bus segment 2, through bus segment 3. But how do we bring it back to the test set? Well, we would apply a jumper across the end of the busway system. So for instance, here I show jumping from the A phase to the C phase. Now current can return through the 3 segments on the C phase, and to bring it back to the test set, I connect the C2 leads back into the instrument from the C phase. Now we can see the current loop that is going to be produced. So now let's say I want to take the total series resistance of the A bus. Well, I work with my potential lead. So the first potential lead, P1, I connect onto the A bus. That's the one I'm interested in measuring. But now, how do I bring this signal back or measure across all 3 segments? Well, at the far end, I provide a jumper from the A bus to the B bus. Okay? So I'm basically now using the B bus as an extension to my test lead to bring it back to the test set. And I now connect my P2 lead to the B bus. Effectively, remember earlier I told you since the current loop is a measured value and the potential drop is a measured value, lead length is not going to become a factor in my measurement. So effectively in this configuration, I am only measuring the voltage drop from the P1 to the 3rd section of the bus bar, or where the jumper is placed at the end of segment 3. And now I can take a very accurate measurement of just the A bus and all of the through-bolt connections. All right, now next let's take a look at doing the insulation resistance measurements. Now here we would use a device like the megometer, insulation resistance test set, or sometimes simply just referred to as the megger. Okay. Now here, basically the way this test set is going to operate is we are going to apply a known voltage across 2 conductive surfaces that are isolated by an insulation. Okay. So we put a known voltage across. We measure several currents, capacitive charging current, which starts high, drops relatively quickly, absorption current as the insulating material goes through polarization. And effectively, when this all occurs, we then measure what's known as the leakage current, the current of most interest, the current that's traveling through the insulation, which should be a very, very low current if everything is good and healthy, and applying a known voltage, measuring a leakage current. Through the magic of Ohm's law, the instrument displays the resistance. In this case, leakage current should be very, very low. Therefore, resistance should calculate out to be megohms and greater. Okay. Now, as we look at in this diagram, when we measure the resistance, we are connecting between either a bus bar and ground or frame, or we're connecting between a bus bar and bus bar, for instance, in a phase to phase. These are parallel resistances. So let's take a closer look at this now. Again, if we were to measure the insulation resistance of a single segment, phase to ground or phase to phase, okay, we would come up with obviously a resistance value for that segment. Now, as we assemble this busway and we add another segment, watch what happens. So we add another segment. In essence, we are now measuring the resistance of segment R1 plus the resistance of segment R2. But look, these are parallel values. Therefore, the total resistance of segment 1 plus segment 2 is the reciprocal. We have to take total resistance is going to equal 1 over the total resistance, which is going to equal 1 over the resistance of R1 plus 1 over the resistance of R2. If we add a third section, again, it adds up as reciprocal value because we're dealing with parallel resistances. And that is the way our insulation resistance measurements are going to add. Now, as we go into actually calculating these numbers, when you add these, what you will find is that your total resistance will always calculate to a value that is lower than any of the isolated sections by itself. So again, if you had 3 sections of a bus pre-assembled and they each tested at 10 megohms, when you connect the 3 together, you're measuring parallel paths. It will not add up to 30 megohms. It is going to be some value less than 10 megohms. It will always be lower than the lowest section value. But let's go on and make some calculations. So prior to installation, each section of busway was tested in this particular model, and the individual insulation resistances were recorded, as seen in this illustration. So what is the insulation resistance value for the installed busway system? Well, remember, we need to add these up as reciprocal values. So take a moment and add these values. Type into the chat what your final number comes to. And let's take about 30 seconds to do this exercise. Okay, well, again, the resistance in megohms would equal 1 over the total resistance, which is going to equal 1 over 5,000 ohms plus 1 over 3,000 ohms plus 1 over 3,000 ohms, so on and so forth. If we go through the calculations, you should have come up with 1 over 0.002126, and we take the reciprocal of that, and we would see that this total resistance in this bus section or system comes out to 470.37 megohms, depending upon how your calculator did the rounding. But you would have come up with a value somewhere around 470 megohms. Now, if we go to the NETA table 100.1, as we recall, let's go back here, this is a 600 volt busway, okay? So if we go back to the NETA table for nominal rated equipment, 600 volts, minimum DC test voltage would have been done at 1000 volts when we were doing our insulation resistance test. And the recommended minimum insulation resistance in megohms in table 100.1 shows that we should fall within 100 megohms. Now, we added up all of the resistances of all the bus sections, and we saw that the total resistance in that assembled busway was 470.37 megohms. So, based on table 100.1, did we pass? Is this busway section good? Or did we fail? Type into the chat. What do you think? Is it a pass? Is it a fail? Or do we not have enough information to know yet? Type into the chat what you think. All right, let's move on. Again, 600 volt bus system. Now let's assume what are the lengths of the bus. So here we show that we have 150 feet, then we take a 90 degree, we travel another 100 feet, we take a 90 degree, we travel another 50 foot. The key thing we need to remember here is when dealing with Table 100.1, this table, the values that are in there, particularly when dealing with busway systems, is based on lengths of 1,000 feet. Now remember, as length gets longer, we're adding parallel resistances. Therefore, we need to correct our measured megohm value, or measured insulation resistance value, to a nominal length. Now, in the NETA table, it is based on 1,000 foot lengths. So, the correction would be R sub 1,000 feet, or the correction resistance would be the measured resistance times the length of the run divided by 1,000. And that will correct our answer for the NETA table. So, if we do this, we take our 470.37, which was our measured resistance, times the 300 feet of total length, 150 plus 100 plus 50, divided by 1,000, since the NETA table is based on 1,000 foot lengths. And we would see that our actual recordable resistance for our report would be 141.1 megohms. So going back to our NETA table, we see that we need a minimum of 100. We came in at 141. Therefore, this definitely would have passed. However, let's take the same measurement, but with different lengths. So what if, rather than the previous length of 300 foot, what if this was actually shorter? 75 feet, 50 feet, 25 feet. Well, again, we go through the same mathematics, the same correction factor. So here we would have the 470.37 times 150 combined feet divided by the 1,000 feet for our correction factor. And here we would see that the actual resistance that we're comparing into table 100.1 is only 70.6 megohms. Now again, based on the recommendation, NETA table 100.1 for 1,000 foot values wants to see a minimum of 100 megohms. After applying our correction factor, we see that really we only have 70.6 megohms, and this actually would have been a failure. So the point that we're really trying to emphasize here is when dealing with the busway systems, as they become assembled and grow in length, we always have to take into consideration what is the length before rendering what is the insulation resistance value. Again, table 100.1 in the standard is based on 1,000 foot lengths. So we need to correct for that in our measured value. And here we see length definitely would have mattered. In the shorter example, we see that this would actually have been a failure, even though the initial megometer reading of 470 looked very, very good. Once we corrected it to a nominal 1,000 foot length, in reality, we did not pass the recommended value in the NETA table. Now, let's also look, though, at NEMA standard publication BU1.1. NEMA standard publication BU1.1 specifically addresses busway rated for 600 volts and less. and NETA is the National Equipment Manufacturers Association. So in essence, this is very similar to manufacturer's recommendation. Now, here we see the NEMA standard specifically addresses busway rated at the 600 volt or less. Here we also see NEMA provides a recommendation or a recommended resistance value of 1 megohm for a 100-foot busway run. Okay, so might want to write that down. We're going to come back and reference it later in our webinar. But NEMA recommended resistance value is 1 megohm for a 100-foot busway run. And this would apply to all 600 volt and lower class busway systems. So now let's go back to our exercise once again. Here we have a 600 volt busway system. Remember, under the NETA table, this example failed, okay, because of these short lengths, 75 feet, 50 feet, 25 feet. So under the NETA guidelines and table 100.1, remember, this had failed. Let's see how it compares to the NEMA recommendation. So now we correct for 100 foot. So we take our 470, our 150 feet of actual length, divide it by 100 foot on our correction, and we come up with 705.6 megohms. Now, based on the NEMA recommendation, which is manufacturer's recommendations, or NEMA, the National Electrical Manufacturers Association recommendations for resistance values, we are well within the past parameters. So here we need to understand sometimes where the NETA tables may apply, and as the NETA manual always refers to us, when manufacturer's values are not available, our tables are there for reference. Well, we can accept the NEMA table as manufacturer recommendation. And for 600 volt class busway and lower, the BU 1.1 specifically addresses this with the necessary recommendations. So again, know what set of standards we need to be using when rendering a pass or fail recommendation to our clients. All right, let's do another exercise here. Here we see an insulation resistance data sheet. And we have some captured insulation resistance values. A to B, B to C, C to A to ground, B to ground, C to ground. And we see the appropriate values that were recorded. So, first question. Based on table 100.1, and notice this is 2,500 volt MCC, as we see under the substation line in the data report. So we got 2,500 volt system, okay, and the values that are displayed, did we pass or did we fail? So again, 2,500 volts, we need to have a value recommended of 500 megohms as the minimum. Do we pass, do we fail, or do we need more information? Well, if you answered need more information, you are correct, because what we have just learned is that length needs to be applied to our decision in order to use the reference tables appropriately. Therefore, we need, if we're using the NETA table, to correct for 1,000 foot lengths. Now, as an example, let's assume that the length of the busway tested is 500 feet. So based on the conversion formula shown, each measured resistance would need to be multiplied by 0.5 in order to obtain the 1,000 foot equivalent resistance. When we do this, we see that most of the measured values are less than the minimum requirement and fail the NETA recommendations. So here we clearly see the B to C would have failed, A to ground, B to ground, C to ground would have failed. Now, let's assume that the length was longer. So now let's assume that the tested busway is 2,000 feet in total length. So now, based on the formula that's shown, we would multiply each measured value by 2. And based on a 2,000 foot busway, we see that all of the measured values are well within the NETA recommendation in Table 100.1, and this busway system will have passed. Once again, we see how important it is to correct for length. All right, now here we see a distribution switchgear data sheet. But as part of the distribution switchgear data sheet, it also has an area for insulation resistance measurements of the bus sections. A to B, B to C, C to A to neutral, B to neutral, C to neutral, A to ground, B to ground, C to ground, and neutral to ground, and so forth. Okay? Now, here we see that this voltage class is, I believe, we're using 5,000 volt class. Yes, here we go. 5,000 volt class system. So, notice that we are using this distribution's switchgear data sheet as opposed to the one earlier. Now, based on the reading shown, did the busway pass or fail the insulation resistance test? Okay. So, are we pass or are we fail? Well, once again, what we learned is we need more information. We have not addressed length yet. Okay? Now, if we are testing the bus bars that are inside the switchgear cabinets, the verbiage in the NETA, ATS, and MTS procedures under distribution switchgear does not necessarily address or specify the correction factor. But if we are testing the bus bars inside, we can refer to the recommendations for testing busway. And we obviously had seen the correction factor for 1,000 foot nominal runs is necessary in order to get an accurate comparison to Table 100.1. So, let's go based on the readings that are shown here. The bus inside the switchgear are possibly in the order of maybe 30 to 50 feet. So based on this type of length, if we were to apply the correction based on length, we would expect insulation values closer to 200 megohms. Okay. So this raises a question. Was the switchgear isolated from the incoming and outgoing bus? And are we dealing with just these very short sections inside the gear? Or was the incoming and outgoing connected to the remaining of bus systems, in which case we might be talking significantly longer busway systems? As we learned, we need to know the length in order to get a good comparison to the reference tables. So, again, length is going to matter in our overall measurement, and we're going to need to be able to correct accordingly to get an accurate comparison to the reference tables. So, as an example, let's assume that the length of the busway tested was only 50 feet. Only the bus inside the switchgear section. Based on the conversion formula shown, each measured resistance would need to be multiplied by 0.05 in order to obtain the 1,000 foot equivalent resistance. When we do this, we see that all the measured values would fall below the 1,000 megohms and would fail in the comparison to the NETA recommendation. Okay. The highest of the values would only have calculated out to 216 megohms. So again, for the 5,000 class gear, we would want to see 1,500 or 1,500 as the minimum. By applying our correction factor to, if this was literally only a 50-foot section, once we applied our correction, we see that we fall significantly lower than the recommended megohm value, and this would have failed. Now let's talk a little bit about determining length. If performing an insulation resistance test on this busway structure, what length would we use in order to convert our readings to the 1,000 foot nominal value? So we've got 200 feet going out from the gear. We see that coming out, tapped into it, we have two sections of 100 foot. We have a 90-degree turn, which extends another 150 foot. What length would we use if we were testing the insulation resistance of this entire bus structure? So again, based on the bus structure shown, what busway length would we use if we were to perform the insulation resistance test? Now, if you answered 550 feet of total length, you would be correct. So 200 foot plus the 150 foot would bring us to 350 foot, plus the two 100 foot sections, so that would be 450, and then finally 550 feet total combined length, as we see here. So, in summary, a bus bar is a conductor that serves as a common connection for two or more circuits. Busway is defined by the National Electrical Manufacturers Association, or NEMA, as a prefabricated electrical distribution system consisting of bus bars in a protective enclosure, including straight lengths, fittings, devices, and accessories. Resistance measurements recommended by NETA include: perform resistance measurements through bolted connections and bus joints with a low resistance ohm meter, also known as micro ohm meter, digital low resistance ohm meter, DLRO, or also sometimes referred to as adductor. Perform insulation resistance tests on each busway, phase to phase and phase to ground. The total resistance in a series circuit is equal to the sum of all the parts of that circuit, as shown in the equation. The series resistance would be, the total resistance would equal R1 plus R2 plus R3, and so on and so forth. The total resistance in a parallel circuit can be found using the equation. The resistance in megohms would equal 1 over the total resistance, which would equal 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth. The installation resistance of each busway section add as parallel resistances, and thus the total resistance of a completed busway system is always less than the lowest resistance section measured prior to the installation. Minimum resistance values listed in NEMA Table 100.1 are for nominal 1,000 foot busway runs. Therefore, all of our measurements need to be corrected to the 1,000 foot nominal value before using the NETA table. NEMA standard publication BU 1.1 specifically addresses busways that are rated 600 volts or less. And since NEMA is the National Electrical Manufacturers Association, this would be manufactured recommended values. Now, the NETA correction factor for length is going to correct to 1,000 foot. So the measured resistance times the length of our run divided by 1,000. Whereas NEMA BU 1.1 provides a recommended resistance value of 1 megohm for a 100-foot busway run. The megohms would equal 100 divided by the length of the busway. And that concludes our Third Thursday webinar for this month. Again, I'd like to thank you for your attendance. We always love seeing, our friends join us during these webinars. We truly hope you find value in them. This was a rather interesting one. I was kind of inspired to do this particular webinar based on my days reviewing data sheets during various service jobs for the service company that I was working for. And all too many times, one of the common mistakes that were made was simply going out there, taking insulation resistance measurements, documenting on the spreadsheet, but never properly using the NETA tables and correcting the measurements for length. So it was such a common mistake, particularly with new technicians that had not really reviewed the NETA documents or had received training yet. It was a common mistake made, and I felt it would make a good webinar for our month. So I hope you enjoyed the resistive testing of busway systems. Did it pass or did it fail? Hey, without further ado, let's get to those questions.